All right, so welcome to Saturday Physics for Everyone, the last Saturday Physics for Everyone of the season. So thank you all for coming out here. I'm glad it wasn't cold and snowy, just kind of warm and rainy. Yeah, everyone have a seat. There's tons of room. We had our 30th anniversary for this program a few weeks ago. I know some of you have come to these many times. We really appreciate it. I think it's a great opportunity to show people what kind of stuff is going on in the physics department and to answer questions that people in the public have about the universe, about stuff that we work on. So I think these are a lot of fun. I am Jeff Filippini. I'm our speaker today. I'm an associate professor here in the physics department with a courtesy appointment over in astronomy. And I have the unenviable task of having to introduce myself because the person who should be up here introducing me got sick. And so he'll feel better, it'll be great, but that means I have, it's very, the very awkward task of telling you how great I am. It won't take long. So I'll be talking about ballooning, Antarctica, and the baby pictures of our universe, and hopefully we'll have some fun. So how did I get here? I am from the small town of Stormville, New York, about an hour and a half north of New York City. It's a beautiful community, much smaller than Champaign in the Hudson Valley area. Then I went to Harvard, where I studied chemistry and physics as a glutton for punishment, and worked a little bit for my senior thesis on underground particle physics detectors. That led me in grad school out to Berkeley, where I worked on an experiment called the cryogenic dark matter search, where we built ultra-sensitive, ultra-cold detectors operated in a mine half a mile underground in northern Minnesota to look for evidence of unknown particles that might constitute the missing mass of our universe. And this is me up in a clean room bunny suit in that mine underground. As a postdoc at Caltech, I worked on similar detectors to study radiation from our universe, to study the history of the universe. That's what I'll be talking about today. And I've been here at Illinois since fall of 2015. Okay, and then this is me in front of the experiment I'll be telling you about today. We don't need applause for this part. Or questions, what? We're gonna get there, we're gonna get there. Okay, so what I'd like to tell you about is we'll take a little bit of a wandering tour, and feel free to ask questions, through a few things. So I'm gonna start by telling you about the dawn of time, cosmology, the history and structure of our universe on the largest scales, and how we learn about it. Then I'll tell you a bit about our instrument, very, very cold detectors that we use, things we work on here to make the measurements we need to get new understanding about the early universe. And then how we take those instruments to observe from the ends of the Earth, Antarctica, where I was 1 year ago today, and take our instruments to the edge of space on really big balloons. So that's the plan. But in order to talk about cosmology, for an audience that doesn't necessarily know about it, so I remember when I moved out to California to start grad school, and I called my mom and said I was starting to get interested in studying cosmology. There was a long silence on the end of the line. I have a cousin who does makeup and hair. She is awesome and does amazing things. It is not what I do. So we study, as I said, the history and structure of our universe. And to talk about how we study that might sound like a question in philosophy. How do we actually get quantitative information about the deep history of our universe? And to tell you that, I need to tell you two big facts that sort of make all of it work. So the first of these is very simple. Light takes time to travel. So light travels at 300,000 kilometers per second. If you prefer freedom units, it travels at 186,000 miles per second, 1 foot every billionth of a second. So when I talk to you, many of you are about 15, 20 feet away, you are seeing me as I was about 0.0000002 seconds ago. And I'm getting old, I don't move too fast, this is not a big impediment on our understanding. So the friend you see you're talking to when you're saying, who is this guy up front, he's really boring, that person is seeing you as you were a few nanoseconds ago. But in astronomy, these time delays start to matter more. So for example, we see the sun as it was 8 full minutes ago. We don't usually think about that, but we see the sun as it was 8 minutes ago. If you go out on a nice summer night, a winter night, and look up in the night sky, you can see the brightest star in the sky, Sirius. And we see that as it was around the time my son was born, 8.6 years ago. That's when the light left that star. We see that far into its past. And some of the other stars we see are from around, say, Procyon, around the time my daughter was born. And the stars in Orion, hundreds or even over 1,000 years ago. So when we look out into space, we look into the past. And sometimes very extreme past. When we look at the Andromeda Galaxy, which you can see as a little fuzzy patch in the sky on a clear night, we're seeing it as it was around the time the genus Homo emerged in Africa, the first humans, depending on how you count. When we look at the Perseus cluster, the biggest known mass of galaxies in the universe, this is an image from the Euclid Space Telescope, released just a few weeks ago. We see that as it was around the time the first dinosaurs emerged. And if you zoom in on pick a little, any random region of this plot and zoom way, way in, which you can with this incredible image from the space telescope, you can see that it is peppered with galaxies, tiny because they're far away, incredibly distant. And some of them, which you may not be able to see from the back, there are some little red dots, very small. Those are also galaxies, seen as they were literally billions of years ago. Some of these galaxies, the light was released before the Earth was formed, before the sun was formed. And so because light takes time to travel, we see into the past. So like archaeologists or paleontologists, we have fossils that we use to study the history of our universe. But we don't get to pick them up and play with them. We can only see them through our telescopes and try to understand what they mean. Okay? I should note in passing, because it's going to matter, why are those very old galaxies red? So the reason they're red is the Doppler effect. So this is the same effect that you may be familiar with if you've had, an ambulance drive by and you hear the sound change as the ambulance passes you. It goes from high-pitched when the ambulance is approaching to low-pitched when it goes away. This sort of meow kind of effect. That is because of the Doppler effect. That's because an object that's emitting waves, whether they're sound waves, water waves, light waves, anything, it catches up with the wave fronts in the direction it's moving, and they are stretched out in the direction behind the object's motion. So what that means is things moving toward you appear at higher frequency, and when something's moving away from you, its light and sound appear at lower frequencies. And this happens with light as well. And in our case, we see various spectral features. So these are little lines, dark lines in the spectrum of light that comes from a distant galaxy. They're fingerprints of particular chemical elements. So we know where all of those dark lines ought to be. We see them in nearby galaxies and stars. When we look at these distant galaxies, not only does the galaxy look redder, those lines are in the wrong place. They are shifted toward the red, red shifted. They appear at longer wavelengths, lower frequencies. That is the Doppler effect. That tells you the reason these galaxies look red is because they must be moving away from us. And it turns out the farther away the galaxy is, the faster it's moving away from us, which is pretty weird. This was discovered about 100 years ago, a little less, by a scientist named Edwin Hubble, working at the 200-inch Palomar telescope in California, but then for many years, the largest telescope in the world. And the only conclusion you could come from that is that the universe is expanding. This is what we mean when we say the universe is expanding. When we look at things that are far enough away, so not you and me, and not even things like the Andromeda Galaxy, things much, much farther away, millions and billions of light years away. Remember, light year I didn't say this, light year is just a way we talk about really big distances. It's how long does light take to reach you. So the sun is 8 light minutes away, the Andromeda Galaxy is 2 million light years away, and these distant galaxies are billions of light years away. So the way to think about this, the way to think about why these galaxies look red, is that if you imagine like putting the galaxies as little dots on the surface of a balloon and then blowing up the balloon, space is growing and growing and growing, expanding between the galaxies. So they all seem to be rushing apart. It's not that we're in the center. Every dot on the surface of a balloon would see every other dot moving away. So the universe is expanding. It seems to be expanding uniformly. Wherever you stand, you should see that same expansion. And that means that more distant objects look red because they are rushing away. They appear to move faster the farther away they are. So why is this important? So this expanding universe is that second fact. And the reason it's very, very important is because looking into the past wouldn't be all that interesting if the past looked exactly like the present. But because the universe is expanding, the past didn't look like the present. So the universe was different in the past. It had to be to see this expansion. And we can see those differences. So that's sort of the beginning, the core insight of observational cosmology, that you can see our history, and our history is not the same as our present. You can see the universe developing. And so this is when you build an instrument like the James Webb Space Telescope that you've heard in the news, JWST, that was launched some couple of years ago on Christmas. It is designed to have an enormous mirror to collect a lot of light from incredibly dim objects very, very far away. It's designed to observe in the red and the infrared to see the very long stretched wavelengths of some of the oldest objects in the universe, the first galaxies, the first stars. And when an instrument like that, or any of our other telescopes, looks out into space, we can see earlier epochs, like the beginnings of the first galaxies, maybe even the first stars. So in this sense, as I said, telescopes are time machines. And very importantly, because of that stretching of light, the older things we see as redder. We see them as longer and longer wavelengths. Eventually, something old enough, far enough away, the light would be stretched out of the visible range entirely. And so and we could not see it with our naked eyes, and we would need specialized instruments, like the Webb telescope or things that I'll be talking about today, to see this longer wavelength light and to probe those earlier epochs. Okay, so redder is farther, is older, is earlier. Okay, so one question you might ask, now that you know these two things, we know the universe is expanding, everything's rushing apart, and we know something about physics, at least we like to think so. So we should be able to imagine what happens if we run the clock backwards. What would it have been like in the past? Well, all these things must have been closer together. And if we keep running the clock back and keep imagining what things must have looked like, we can see these older and older proto-galaxies, earlier and earlier forms of galaxies, and we can see that things were denser in the past. And so just from these two facts, it must be that the universe, at some point in the past, if nothing changed, everything should have been all smushed up together as some kind of a hot, dense gas, or in fact, a plasma. So a plasma is what happens when a gas gets sort of hot and squished enough that the electrons get knocked loose from the nuclei and can wander freely. So this is what happens, for example, at the surface of the sun. So if we just follow the logic of the expanding universe backwards, eventually we conclude that at some point in the distant past, again, unless something changed, all of our matter should have been smushed up, and it would be like the surface of the sun everywhere. Pretty weird. But that's what unless something strange happened a few billion years ago we don't know about, this is what you would expect to have been true. The universe should have been hotter and denser. And in particular, if you look at the surface of the sun, you can't see inside the sun. The surface of the sun is opaque. It's a glowing hot plasma. Once you make a plasma, once the electrons get loose from their atoms, the material becomes opaque. Light can't pass through it anymore. So we can see the glowing surface of the sun, glowing with its own heat, but we can't see into the sun with light. So this is what we might imagine. In any direction you look, if you built the right kind of telescope and looked out into space, you should eventually see far enough back, that you see when that neighborhood of the universe was like this. This is, in a sense, what we mean by the Big Bang, the hot Big Bang, like that the universe used to be hot and dense like this and has since expanded and cooled and formed stuff. But this was a central prediction of the Big Bang theory when it was suggested some 100 years ago. that the whole universe, if you just follow the logic, the whole universe should at some point have been like the surface of the sun. And that glow should still be visible. Now, of course, when we look up in the sky, we don't see a glow from everywhere in the sky. It's dark at night, right? So the first glance is that's a problem. Why is it dark at night? I should be able to see this glowing surface everywhere I look. And that's where we get back to that stretching, that redshifting. Those distant places, that light should have been stretched and stretched and stretched by the expanding universe. It would appear at very, very long wavelengths, redder than red, so red that you can't see it with your eyes, only with a specialized instrument. And so the idea was come up with some decades ago that this is a natural consequence of the Big Bang. And in the 1960s, a team of scientists, an eminent theorist, Jim Peebles at Princeton, and an eminent experimentalist, Robert Dicke, decided they should build a radio telescope and try to look for this glow. Maybe it'll be visible out in the radio waves, very, very long wavelengths. And famously, they started working on this project and then got a call from some friends at Bell Laboratories down the street in New Jersey, who said, you know what, we built a really big instrument, part of the early satellite communications process, and we pointed it out at the sky to try to do some astronomy, and there was this hiss, static, fuzz that was in the signal that we can't get rid of. They spent a great deal of time doing things like cleaning pigeon poop out of here, like trying to figure out why is there extra noise in our instrument, and eventually concluded the sky has static, which looks exactly like what the Big Bang Theory predicted. So famously, Bob Dicke gets this call, hangs up the phone, turns to his students and says, well, we've been scooped, boys. And in fact, Penzias and Wilson won the Nobel Prize in 1978 for this discovery in the 60s. And so what you're seeing is the glow of that transition, that moment where the universe goes from being opaque, hot plasma, free electrons, to those electrons snapping into orbits. The universe cools just enough that you form atomic hydrogen, which is now transparent. So it's that last glow, that last scattering surface that we see in every direction all around us. And since then, there have been additional work studying the hot and cold spots that I'll talk about in that light, which were discovered in the 90s. And then there's a faint degree of polarization of that light that was discovered some 20 years ago. So if you could build a telescope to look at the cosmic microwave background, and only the CMB, and make a map across the sky. Imagine making a map of like a globe, but you're inside the globe. So you flatten it out. So you have a map of the sky. It would look incredibly boring, which is also remarkable. This glow is incredibly uniform from place to place. It is almost exactly the same in this direction, that direction, every direction. Which in a sense is surprising, because that light took 13.8 billion years to get to us from over there. And that light took 13.8 billion years to get to us from over there. And the universe is only 13.8 billion years old. So light hasn't had time to get from over there to over there. So it's actually quite surprising. How does that neighborhood know anything about that neighborhood? Why are these neighborhoods the same at all? But they are. We'll get back to that. So this is visible as a 2.7 degrees above absolute zero thermal glow, filling the entire sky almost perfectly uniform from place to place. The glow is brightest at about 160 gigahertz. So this is much redder than infrared. You wouldn't even call this infrared. This is somewhere between infrared and radio. It's in the microwave range. So your microwave oven is a few gigahertz. This is more than that. So, this is much higher frequencies than like Wi-Fi or cell phones, but much lower frequency than infrared light. And this was emitted, I'm sorry, that's a typo, 380,000 years after the Big Bang, about 400,000 years after whatever it is happened at the beginning. If you can make a more precise map of this and zoom in on it, you can see that it's not perfectly uniform. There are hot and cold spots at the level of about 100 parts per million. So micro-degree variations on this 2-degree background. And if you make a map, it looks something like this. This is from the Planck satellite, made about a decade ago. It's the finest map we have across the full sky. And you can see these tiny little hot and cold spots from place to place, infinitesimally warmer and colder. Now, the flat map sometimes confuses people, so I like showing the beach ball version. This is really a projection of what's going on a sphere all around us. So you can see this is made by the team of the WMAP satellite, which was the previous CMB satellite that made this observation across the full sky. And you can see there's a red band down the middle. That's not the CMB. That's actually the glow of our own galaxy getting in our way. That glow has been kind of, so to speak, the scientific version of photoshopped out in this image. Like a real quantitative thing was done. It's not faking. But the middle band of this is really is mostly obscured by the galaxy. But the rest of the sky you can see quite clearly. And these represent spots where the matter was a little more or a little less dense by a tiny amount in that hot plasma. Tiny, tiny seeds over and under densities. This is a baby picture of our universe. Today it is 13.8 billion years old. This is what it was like at 380,000 years. Incredibly different time scale. And of course it looks very different than what we see through our telescopes today. So okay, why do we care? What can we do with this? So this is called, as I said, the cosmic microwave background. You will hear me say CMB. In a sense, it's actually the brightest light in the universe. Most of the light in the universe is CMB light. It's just not light we can see. So if you think about these hot and cold spots, what are they? You're looking at this surface. So the way I like to think about it is it's as if you were looking at the surface of a pond. So there's this fluid you're looking at this surface all around you of when the universe was this hot fluid. And imagine you had a pool of water and you drop rocks in it and you produce little ripples that radiate outward. And imagine you drop lots and lots of rocks, or maybe it's raining. And so there's little pitter-patter of impacts on the water. And there are a crisscrossing of these waves such that the surface just looks rough. That's what you're seeing. That's one way of thinking about what you're seeing. You're literally seeing a snapshot of sound waves that were moving through this plasma, crisscrossing one another. Set off by the Big Bang, set off by something earlier that I'll get to in a moment. And the thing is, if you look at those, if you imagine having a pool of water versus having a pool of syrup, if you dropped a rock in that syrup, the ripples would look different. And you'd be able to tell the properties of the fluid that's sloshing around based on the pattern made by the ripples. Very much like you could listen to a musical instrument. You could play the same note on a stringed instrument, on a piano, or on a signal generator, and there'd be different combinations of overtones, a different fundamental frequency to a particular string of an instrument. You can learn about the instrument. You can tell the difference between a brass instrument and a woodwind based on this exact combination of tones that is in the sound. This is just the visual version of that. I'm looking at a map and figuring out and looking at the pattern of frequencies present in those sound waves to learn about the materials. And most importantly, those little overdensities that are present, that are so tiny back then, grew into all the things we see today. If an area of that plasma was a little more dense, it would have gathered surrounding material under its gravity to grow bigger and bigger and bigger. And the rich get richer, right? And you have this little blob of material, starts off as almost nothing and eventually grows into a galaxy cluster. Everything we see through our telescopes started its life as one of these tiny overdensities. And all the voids between them started out as the underdensities. So again, this is a baby picture of all the structures we see in our universe. So this is the why we care part. So to be slightly more technical, what we do with this map is we look at it and we take what's called a version of a Fourier transform, a spherical harmonic transform. What it really means is ask about the typical sizes of the ripples. Is there more rippliness or less rippliness on different, if you take that map and smooth it on some scale, like draw circles on it that are this big and smooth the map to that scale, how ripply is it? And ask the same question for every scale. And you get something like this. So large scales are on the left, small scales are on the right. So there's a lot of technicalities in math to this, which is super interesting. But this is Saturday physics for everyone, not just people in upper level physics classes. So the way to think about this is very much like what I showed you before of when you look at the tones and overtones in a sound wave. This is the fundamental tone of our universe. That is the dominant sound wave that was moving through that plasma. Shows up on the sky at a scale of about 1 degree of arc. And then these are the overtones. And by studying this spectrum, you can learn about the properties of the fluid, the properties of the sound waves that set the fluid ringing. And this light has also passed by everything on its way to us. And so there's various shadows and signatures you can learn by using this light as a backlight. So for example, this spectrum, there are data points with error bars on here, but you can barely see the error bars because of how good our measurements have gotten. There's also a line through here that shows the theory curve, which goes right through the points because we have a very good understanding of this. This system, that hot plasma with these very, very tiny over and under densities, is actually a very easy, simple system to calculate. Calculating how you form a star or a galaxy, super hard. Calculating how these ripples move in this plasma is actually very easy. So we can do very precise constraints on what things were like at that time. And so you can learn the position of that peak, that fundamental tone, was discovered around the year 2000 and showed us that the universe was spatially flat. Really big triangles have angles that add up to 180 degrees, just like you learned at school. It didn't need to be that way. The universe could have been curved like a ball, and it's not. The slope here tells you how much ordinary matter there is in the universe: protons, neutrons, electrons. And that only about 5% of the total is stuff we understand. And the ratios of odd and even peaks turn out to tell you that most of the matter that's sloshing around in these sound waves isn't protons, neutrons, and electrons. It's something else, something we call dark matter. And I talked about that in my last Saturday physics talk some years ago. So we'll skip that for now. Suffice to say, you learn an enormous amount of quantitative information from this. But one question you might have is about those sound waves. How did you set up what all this is? Why are those overdensities there? Why is the universe so uniform across the sky? And our best understanding of that is a theory called inflation. So I won't get into too much detail about that. There are theorists like Professor Adshead in our department who study this in great detail. But the idea basically is there is a well-known, if surprising, effect where a certain kind of particle physics quantum field, if it is present in the early universe and is the dominant source of energy density in the early universe, it will cause the universe to briefly expand incredibly rapidly, like growing by factors of 10, e to the 60th. So very, very large numbers, in fact, many, many orders of magnitude in a tiny fraction of a second. And then this particle decays and the expansion stops. And what that does, there are many ways for this to happen. It sounds wild, but there are very clearly understood physics ways this could happen. And if it did, it explains a lot of the weird stuff. It explains why the universe is really boring on large scales. Why is the CMB so homogeneous? Why do different places in the universe look so similar? It's because whatever wrinkliness and non-homogeneities were in the early universe have been smoothed out. You've inflated the universe so much, just like we can't see the curvature of the Earth when we're standing in a room because we see only a tiny portion of it. Whatever curvature and nuttiness was going on in the early universe has been expanded so much that now we're like ants looking at only a tiny local piece, and so everything looks very uniform to us. Because we are linking very tiny things suddenly become very, very big, quantum physics, quantum fluctuations are imprinted on the universe. You actually get density fluctuations. This is the source of all of those little hot and cold spots. What set those sound waves loose in this picture is quantum noise that was sort of blown up and imprinted on the universe. And so that led to those sound waves and led to all those galaxies and thus to us. Cool. But the other thing this tells you is there's another prediction of inflation, which is that same noise that was imprinted in the universe's sound waves was also imprinted in gravitational waves. There should be a hiss of gravitational waves, ripples in space-time itself, the same things that LIGO detected, but today much, much fainter, should have been created. And that hiss of gravitational waves is a unique signature of inflation. And if you could compare the brightness of the gravitational waves to the sound waves, that would tell you about the exact physics that went into this inflationary epoch. What was really going on in those first moments? At energies far beyond anything that any particle accelerator could achieve. You'd have this unique window in the early universe if you could see these gravitational waves. But, as I said, they're far too faint to see in something like LIGO or nanograv or things like that. And so it turns out they are visible, they're evidence to be visible in the cosmic microwave background. And I'm going to elide over this pretty quickly, but it turns out when we map the CMB, everything I've shown you is just how hot or how cold, how bright is the light from different places in the sky. You can also ask, what direction is the electric field of the light wave vibrating in? There's a small degree of polarization, just the way your sunglasses are polarized to only let in certain directions of light, so it reduces glare from water or something. A similar thing can be done. We can make our detectors polarized and make a map of the direction of vibration of the light coming to us. And there's a particular pattern. The sound waves predict a certain pattern of that polarization. The gravitational waves predict a different pattern, a twisting pattern. And I'm skipping over a lot of annoying math. But the short answer is, if you could see this twisty pattern in the polarization of the light, if you could make this map and saw an incredibly faint pattern like this in the polarization, that would be proof that you saw these primordial gravitational waves. That would be unambiguous evidence for inflation and allow us to quantitatively probe the physics going on in those unimaginably early moments in high energies. And so that's the picture. You have our history of the universe. We start off really hot in who knows what happened. We have inflation, sets forth quantum fluctuations, which sets sound waves and gravitational waves loose into the universe. Then the universe expands and cools and forms nuclei and atoms and stars and professors. And eventually, the sound waves, we got that. We are those sound waves. But the gravitational waves are incredibly faint today. We look for them using a detector that the universe gave us, the cosmic microwave background. This universe-filling plasma is way bigger than any detector we can build. And so if we can detect that faint signature in the polarization pattern, that will let us do what would otherwise be impossible, to observe these primordial gravitational waves. All right, so I'm going a little slow, but that's the lead up. That's what we're trying to do. And there are many, many other things we can learn from the CMB, but this is one thing, often called the holy grail of cosmology, which it's really hard. And why is it hard? It's hard because the signal's incredibly faint. We're talking about micro-degree fluctuations across the sky, less. And power levels, each detector would get the glow falling on these detectors. The pattern would correspond to power fluctuations of like a millionth of a millionth of a millionth of a watt. Not much. How do we build something sensitive enough? We're looking through the atmosphere. The atmosphere absorbs at these wavelengths. The atmosphere glows at these wavelengths. The atmosphere gets in our way. Astronomers love the atmosphere, but they hate it when they're doing astronomy. We like to breathe, but we like to be able to see also. And finally, our own galaxy, the Milky Way, is emitting light at these wavelengths and can mimic our signal. So everybody's got to deal with these problems to try to do a measurement. And so now let's get to a measurement. So this is the instrument that my group at Illinois has spent a bunch of time working on in the past few years. It's called SPIDER. The origins of the name are complicated. It is a balloon-borne instrument to look for this signature and distinguish it from the glow of our own galaxy and of the atmosphere. We flew it once in 2015, mapping the sky at 95 and 150 gigahertz. The second flight was 1 year ago, almost exactly, in Antarctica, where we added another camera at 280 gigahertz, and I'll say why. So this project is supported by NASA primarily, and our trip to Antarctica is supported by the National Science Foundation's Office of Polar Programs. And this is us. This is not a small team. This is a group of people. And this is actually only a fraction of the team, the part that went down to Antarctica this past year. Many more people worked on this project. And that we're in front of Mount Erebus, the southernmost active volcano in the world. And this round of the project, I served as the principal investigator, which basically means I filled out a lot of forms. It doesn't mean I did the most work. So lots of people did this. And I should note there's some Illinois representatives here, graduate students, Sho Gibbs and Ellie Shaw and me, and Ricardo was a former postdoc here. He's now up at Northwestern. Okay. So how do we solve our problems? How do we detect these incredibly faint powers? So the way we do this is something called a bolometer. So a bolometer is a very simple idea. You want to measure a very faint source of light. So think about it like you close your eyes and you're in front of a campfire. And you want to tell where the campfire is. Well, what you would do is you would hold your hand out, you'd move around, and at some point you'd feel the warmth of the campfire, and then it would go away, and you'd scan your hand around, and you could feel that in some directions you get the warmth and some you don't. A bolometer is exactly like this. It's a small absorber, an antenna or something like that, that is thermally isolated from its surroundings and has a thermometer on it. And so when light falls on it, it will heat up a little bit, and we measure that with a thermometer. So as we scan our instrument across the sky, we'll see fluctuating temperature in that device, in that absorber, and that will tell us the changing brightness of the sky. And you can make these extraordinarily sensitive if you get them cold enough that there isn't thermal fluctuation noise. And the thermometer we use is a superconducting thermometer, a transition edge sensor, a little flake of material held on the transition from having zero resistance, superconducting, to jumping up to normal resistance. So very, very tiny temperature changes cause big changes in electrical resistance that you can easily detect. These are the same kinds of technologies that are used in the condensed matter labs or in quantum information labs, but we use them to observe the sky. And to give a particular example, this is an old-style spider focal plane, and I have, I'm not going to pass it around, but if anyone wants to look later, I have one of the prototype wafers here. So it's a silicon wafer, a big microchip, patterned with superconducting wiring, and if you zoom in on one of the sensors, you would see an antenna to absorb light at 150 gigahertz, which would focus that energy onto this tiny suspended flake of material, 0.3 millimeters long, suspended over a pit in the silicon by these incredibly spindly legs. That's the thermal isolation, so that changes in the light on the antenna will change the temperature of that device by a measurable amount. And here's our superconducting thermometer over here. And to give you an idea, the room temperature is what is 300 Kelvin, 300 degrees above absolute zero. This is a degree of the same size as a Celsius degree. So Antarctica, the coldest it ever got was about 184 Kelvin, very, very cold, negative a lot Fahrenheit. Liquid nitrogen, liquid helium, SPIDER keeps its detectors at a fraction of a degree above absolute zero to get the noise required. And we do this on a balloon. So this that you see, SPIDER here, each of these telescopes is about 1 foot in diameter. This is over 1,000 liters of liquefied helium gas that keeps this thing cold. It's the largest such cryostat, cold tank thingy, ever flown on a balloon. It has 6 telescopes, which I'll show a bit more, or a total of over 2,000 of these superconducting bolometers. And the whole thing is designed not just to hang from a balloon, but to point. So it has actuators and sensors to be able to point at any given spot in the sky in azimuth and elevation, so we can scan and know where we're pointing as we go. It had all this shiny stuff is to shield against the sun. Once you get up to high altitudes, anything that's in the sun bakes hot, like in space, because you don't have air to help cool you off. And anything that faces the blackness of space gets very cold. So thermal management is a huge issue here. And the total weight has solar panels for power, and the total thing weighs about 3 tons. The telescopes look something like this. This is what we spent a lot of time here at Illinois, was on these telescopes. So the detectors I showed you are here. They're located behind lenses. This is made in the aerospace engineering machine shop on campus. Somewhere in aerospace, somewhere in mechanical. So these are just lenses made with material that's opaque to visible light, but transparent to microwaves. And the whole thing is kept cold by this liquid helium to limit the glow of the instrument itself, which provides stray light we don't want. And it's housed in this giant cryostat, and here are all these pointing systems and sun shield. So why would you work on something so big and then hang it from a balloon? That seems scary. The reason is because the atmosphere gets in your way. Even at microwaves, there is some absorption and emission from the atmosphere. We're used to the idea that we can see the sky very well at visible light, because the atmosphere is extraordinarily transparent to the light that we see. Probably evolution has some hand in that. We evolved to see the things that we can see through the air, things the sun is good at emitting. But it's a little harder in the microwave. And this is, I'll skip all that. What's happening, the biggest problem is actually water, vibrations and rotation of water molecules. So to observe the CMB, you want to be as high and as dry as you can be. The best observing sites on Earth are South Pole Station, the Atacama Desert in Chile, or, if you have $1 billion to spare, space. We do not have $1 billion to spare, so we try to do the next best thing to space, which is ballooning. So ballooning, the idea is we talk about balloons flying at a height of about 35 kilometers, so 20 some odd miles, much higher than a commercial airliner, up in the stratosphere. The air is incredibly thin, above about 99% of the atmosphere, and so this is a space-like observing environment for us. It also has a lot of the problems of space, thermal management. You have to be very, very lightweight. It has to be very automated, because for much of the flight, you literally only get to text message back and forth with it every minute or so. Literal 255-character SMS text messages. So the automation is a very big challenge here for this complicated instrument. So you get up there on these balloons, and I want to give a sense of the scale of the balloons. This is what the balloon looks like when it's launched. There's only helium in the top portion. When it gets to altitude and the pressure is lower, that helium will expand out, lower pressure, and fill the balloon to stadium size. So when it launches, it's taller, well taller than the Washington Monument, some 850 feet tall off the ground. And when it's at float, it's that says 460. Our balloon's more like 430 feet across, only. And for comparison, the State Farm Center is 400 feet across. So imagine the State Farm Center being a giant balloon, a little bigger, and extending hundreds of feet into the air. And yet, the plastic it's made of is roughly like saran wrap to hold those tons of weight, that vast volume of helium. They do not let us scientists anywhere near that balloon. We would break it. But there are trained professionals who handle these things. Why do we go to Antarctica? We go to Antarctica for a couple reasons. One, this beautiful circumpolar wind pattern. Antarctica is a convenient circularly shaped plot of land around the South Pole. And if you launch in December, summer down there, winter up here, you get to stay over solid ground for extended periods of time. And you don't go over populated areas, and you don't go over countries that might object. We can't do this at the North Pole because we'd fly over Russia, and Russia does not like NASA sending things flying over their territory. You also get 24 hours of sunlight, which is very helpful, not just for power, but because it reduces stress on the balloon. If you launch in other places in the world, there's a day-night cycle where the atmosphere heats and cools, and the balloon will rise and fall, and it'll actually squeeze the helium out. And so the balloon has to be open at the bottom to allow it to avoid having too much stress on the plastic. And a balloon will crash after a couple of days if you launch it from mid-latitudes, at least this kind of balloon. Okay, so what's special about SPIDER? Remember this problem, the glow of galactic dust. This is a map of galactic dust's polarized glow. That glow can mimic our signal, and it is brighter at higher frequencies than at lower. This is the CMB's spectrum as a function of frequency. This is the glow of dust. This is the glow of electrons spiraling around magnetic fields. In order to distinguish this, we need to measure at multiple frequencies, multiple colors of light in the sky to try to deconvolve what it is the real CMB and what's our own galaxy. Unfortunately, these higher frequencies, where it is best to map the dust, are not visible from the Earth. So we have to get above the atmosphere. Satellites can do that, but again, don't have $1 billion handy. We can do it on the ground. And this was what the U of I group on SPIDER spent most of its time working on, developing a new set of telescopes, a new set of receivers with these lenses and built with carbon fiber trusses and things like that, put together in our lab. This is my recent graduate, Ellie Shaw, who just got her PhD a few weeks ago, and Callie Roy Papas, recent undergraduate, who's now a grad student at MIT, putting together one of these telescopes. And they are going to give this unique information on galactic dust at this higher frequency you can't get from the ground. That'll help us understand both SPIDER's own data and produce a map of dust that's going to be useful to everyone else in the field. So now I'm going to show a whole bunch of pictures of what do you do when you build these things. So there is years of work in building and testing these receivers, making sure they do what you want, fixing problems that you have, and getting the big cryostat ready. So this is at Illinois, this is at Princeton, getting things together. Then you get told, if you're lucky, we had to wait 2 years during the pandemic when there were no ballooning flights. But we got the call last April that if we could get ready really fast, we could go. And so we took everything down to Palestine in East Texas, where there's a ballooning facility, Columbia Scientific Ballooning Facility, named after the ill-fated space shuttle, where the team spent the summer in the Texas heat doing a dry run for Antarctica. Everybody goes there. You pull everything out of shipping containers. You pack it all together. You build the payload. You put in liquid helium. You get it cold. You connect it to NASA's electronics and prove that it all works. And then NASA gives you the checkbox and says, you guys are legit. You can go. Then you shove everything into shipping containers and send them on boats and planes to Antarctica. So this is where a lot of my team was last summer. And then this stuff goes to McMurdo Station, which is in coastal Antarctica on a volcanic island. This cross is from one of the earliest Antarctic expeditions where one of the team members died. This is the grave of a team member from an expedition around 1912, if I recall. And this is McMurdo Station. It's kind of like a grungy mining town, but it's a lot of fun. So we all head down there, head out to the Long Duration Ballooning Facility, a set of hangars on the edge of town, a few miles away. You can see Mount Erebus is over here. Oh, there's Mount Erebus. You unpack the cargo. Everybody flies in on military transports, C-17s or C-130s, bundled up in our standard issue cold weather gear. The cargo gets delivered, and then we set to work. So this all happened around Halloween of last year. And everything had to be unpacked. You have to bring your own hardware store. There's no hardware store in McMurdo. If you need a certain size of bolt, you better have brought extra. And we did. So this is putting the instrument together, getting it all ready. People are, a little bundled up, even inside the high bay. Getting the detectors ready to go. This is showing you one of these things, the telescopes being assembled, the cryostat getting mounted on the carbon fiber frame. This is Ellie in front of it, getting this payload built up. The frame supports it, hangs it from the balloon, and allows it to scan. These are all the electronics that read out the detectors and thermometry. It's a lot of work. It's incredibly fast-paced. You do get to have some fun. I've seen some most incredible scenery you can imagine. This is an iceberg field. It's hard to tell, but this iceberg is just visibly blue, sticking up out of the frozen ocean. It just was remarkable. There's all kinds of fun stuff. We get to go on walks when we're not working, which is rare. Some of us grow unfortunate facial hair. It's a good time. And occasionally you do see local wildlife. This was a visit in the first campaign by an Adelie penguin, about yay big, 2 feet tall. We also got a visit by an emperor penguin, which is larger, but I didn't get nearly as close to it, so my pictures sucked. And we saw lots and lots of these guys lounging around in the ice, Weddell seals. So you're not allowed to touch the wildlife. The Antarctic Treaty forbids it, but it's really neat to see them around. And of course, our team, this is the Illinois team when SPIDER was finally ready to go. There are, of course, many more people on the project in Illinois worked on this project. This is the group that was able to go last year. Okay. And one day, after all of this work and a lot of drama with funding agencies and schedules that I won't tell you about right now, eventually, around the middle of December, you're ready to go and get picked up beautifully gift wrapped with Mylar and picked up to pull out. Have the parachute attached. That's the attachment point for the balloon, and you wait. You wait until you go out on a good weather day and wait to see if the wind holds up. Because the way this works is the balloon is laid out on the ground and then lifts up. And so it gets very tall. The wind has to be just so. Absolutely no wind on the ground. Absolutely no wind up at 1,000 feet where that balloon is going to swing to. And most days are not like that. So on days that look good, everybody gets up at midnight, works through to get out to the launch pad by like 9 a.m., because that's how long it takes. And then you wait and see if the weather clears. And if it doesn't, you pack in and go home and hope for tomorrow. But one day, it is enough, and the balloon is getting inflated on the spool. There's the parachute. This is all balloon, just not filled with gas yet. When it's released, the gas will flow down to here. This is a collar. This little piece you can barely see is actually holding the balloon closed at that height, so that when it's released, the helium doesn't like run down and tear the balloon. And in this case, on December 22nd, about 10 minutes shy of the solstice, it was time to go. You can tell we're not as bundled up now, partially because it's midsummer in Antarctica, still below freezing, but not much below freezing. And any day that's a good launch day is a nice day. Perfectly sunny, no wind. So we're not quite so bundled. All right, so let's see what a launch looks like. This is the payload. This is actually our first launch. We had a better video of the first launch than this year's. So here's our balloon, here's our payload, and we are back in that high bay. And we wait until they decide the weather is just so. And so the collar is holding the balloon closed. We are all sitting back here terrified, because things can go wrong. And we've worked a lot of years on this. And so we wait for the balloon. What's supposed to happen is the balloon swings up to be just vertically over the crane, and then the crane backs up and releases it, and it lofts into the sky. That's the theory. So we're all hopping up and down on one leg, nervous over here, and watching that angle. So we want that to be nice and vertical, so there won't be much stress on the payload. That's Spider. The crane's starting to try to catch up, because that angle is starting to grow. The balloon's getting a little ahead of the crane. The wind's a little high. That's supposed to fall. Don't worry about that. That's part of the collar that's holding the balloon closed. And that angle is getting worse and worse. There's enormous stress on that pin. And eventually they say, well, let's go. Bonk. And Spider is released. Fairly violent release. Though honestly, our second flight was more about that's supposed to fall as well. And Spider heads up to the stratosphere. These are pictures from our most recent launch, where we have less good video. And this is a picture from a GoPro camera looking back down at the launch site. And this is a picture from a GoPro at float. The blackness of the sky, our launch was right around here. And that's the camera. That's not what Spider itself is designed to do. What Spider is doing is taking around the world trip. So the blue is our first flight in 2015. The red is our second flight. The red-orange alternations are days. And our altitude is about 35 kilometers, and we scanned about 10% of the whole sky. We landed in December. We landed around the time we ran out of helium in January. This is what Spider's carcass looks like on the snow near the South Pole. And a team came out from the South Pole, picked off the carcass, brought the valuable parts home, including the data, which is the critical part, and brought it back for analysis. This all happened in January. And now we have the data. And unfortunately, the data, there's a lot of work that goes into doing stuff with the data. We start off with basically just little noisy voltage time streams from thousands of detectors. And we have to reconstruct from that where we were pointing, how bright the sky was in that spot, combine the data from those thousands of detectors, remove glitches from cosmic rays and radio interference and things like that. Those are those little red marks. I've got to cut those out of the data, filter it, and analyze it to turn it into maps of the sky. This is from Spider's first flight. showing the hot and cold spots in temperature. And eventually, between temperature, polarization, all of that, you can use it to infer parameters like this number r. These are, for any experts in the audience, these are likelihood plots showing constraints on this number r, which tells you the brightness of gravitational waves. You can tell they're near zero. Zero is within the range, so we set only an upper limit. We did not see the promoter gravitational waves. We simply we constrained certain models of how bright they are. The second flight, I can't really tell you much because the analysis is still in very early days. But I can show a plot from my student Ellie's thesis. This is a histogram of a number called the noise equivalent temperature. It basically tells you the noise level of the instrument projected onto the sky. You want that number to be low. And our detectors, we have hundreds and hundreds of detectors with noise levels of a few hundred microkelvin CMB root seconds. I won't explain those units, but I'll show this plot. This is everybody else that has measured the sky at similar frequencies. South Pole, Akbar, Boomerang was a balloon, Planck was from space, this is Spider. These numbers, 800, 160, 11. Lower is better. Spider is vastly more sensitive, by far the most sensitive such instrument ever put on the sky. And we will have to see how we did as we analyze the data. And so I'm running a little long. I want to make sure there's time for questions. But this is where we are with Spider 2. We're very excited to have this data set to work on. And our team is working on other things. So here at Illinois, we have a very active program in ballooning specifically. We've had 3 balloon missions going. So Spider, I've talked about, is a microwave background instrument. We're spending a lot of our time now upstairs in my lab working on an instrument called TIM. It's a Monty Python reference, yes? The terahertz intensity mapper. This is going to do, I can't talk about this one in detail. It's an entirely different science case. This is an instrument that observes at somewhat higher frequencies, around 1 terahertz rather than 100 gigahertz. And it is supposed to measure the history of star formation in our universe, using particular spectral lines at these frequencies that glow brightly from star-forming clouds. And we'll observe them not just in the modern universe, but throughout deep space and time. That's going to be a very interesting instrument that I hope to tell you more about someday when it's more put together. Right now, we're like banging on a cryostat and trying to figure out why things don't fit together. We're at that stage of the project. Someday we'll be at the stage where we're going to Antarctica. You have to go through one to get to the other. And finally, we have another balloon instrument called Taurus that is designed to, sort of a successor to Spider, that will look at the effects on the light of the cosmic microwave background from the births of the first stars. And I won't go through that in detail other than to say the universe, when the CMB, I talked about the universe being ionized and then becoming neutral, then becoming atomic. Later in the universe's history, the light of the first stars, the ultraviolet they produce, re-ionize the universe. So the universe today is actually plasma again, but so thin and sparse that it's not opaque anymore. But that process of turning on, where the first stars burn off the fog and clear out the atoms and form and reionize the universe, that process is not perfectly understood. Instruments like the James Webb Space Telescope are trying to find evidence of some of the very first stars, some of the first stars that did this reionization. What we are looking at, it turns out that this process actually fogs our view of the CMB very slightly. And so we want to understand this process better so we can understand how to interpret data from cosmic microwave background experiments. And to that end, we built a balloon-borne instrument called Taurus, or we are building, it's in very early stages, that will map the sky at 150 to 350 gigahertz. And this is a collaboration between Princeton, Illinois, NIST, Case Western, and a company called StarSpec that's helping us build the spacecraft part of this. And the different thing about this is it has to measure not 10% of the sky, but almost the whole sky, more like 70% of the sky to do this measurement. And that means we're going to use a new technology of balloon that's been under development by NASA and others called a superpressure balloon, something a little more like a party balloon, slightly thicker plastic, actually closed on the bottom, so it can survive day-night cycles without getting the helium squeezed out and crashing. It can't carry as much weight, so Taurus has to be lighter than Spider, despite being more powerful. But you can do these kind of round-the-world flights over the ocean. This is a flight from 2016 of an instrument called COSY that was up in the air for over 46 days. Launched in New Zealand, Wanaka, New Zealand, went around the world, eventually landed in Peru. And we hope for a flight like that to get long observations of the CMB over nearly the full sky. And we're also working in our group on testing for the future ground-based CMB program. I've talked about ballooning, but most of CMB research is directed toward other things and can be done from the ground. And this effort is at the South Pole and in Atacama, Chile, the best observing sites on Earth. There is an effort across the country and indeed the world bringing together more than 200 scientists to build the next generation coordinated ground-based observing program for the cosmic microwave background. SPIDER, I said, deployed about 2,000 detectors. Across all of multiple telescopes, CMB-S4 will deploy over 500,000 detectors, a much, much more powerful instrument. It will have to look through the atmosphere, but it has power and it has time. And it will be able to do things that SPIDER cannot. It won't be able to measure dust as well as SPIDER or TORUS. That's where we're going to provide new information that they can use. But it will be able to do many things with the CMB incredibly well. And this is an activity at Illinois in the physics department, the astronomy department, and over in NCSA, where there's work going on. Our dilution fridge that Karina and others work on down in our lab in Loomis, where we work on detectors and readouts that are being prototyped for TORUS and for CMB-S4. They're very similar technologies. The astronomical transient pipeline, the things that go bump in the night in the sky, the little flashes that the CMB-S4 will see as it surveys the sky, that effort is being led at NCSA. How will we do astronomy with this incredibly sensitive millimeter wave survey of the sky? And we're all working on developing the science case, all the things this can do. So there's a lot more in this field that I have no time to talk about. But I hope I gave you a little bit of a story of cosmology, like how do we look back to these very earliest moments, what kinds of technologies we use, similar to quantum information actually, though I haven't talked about that quite as closely as I might, and why we take to them, to these extreme locations to get new information about our universe. And so with that, I'm happy to take any questions, and thank you for your attention. Yes?
I think it's really fascinating to see the pictures of people working on these projects, and those are really great photos. It's interesting to think about how many people work on these balloons, and how many people from here work on them, and how many people then would work on these even ground-based detectors. What do you look for when thinking about students in the audience as well? But like, what kind of people work on your teams?
It varies. So the question is, what kind of people work on the teams that go on these kinds of experiments? And it varies a lot. So much of the work done in these experiments, very important thing for SPIDER, these balloon projects are student-driven. So these instruments I've showed you are not being built by professional staff scientists at the national labs. I mean, some of them are. CMB-S4 has a lot of that. But in many cases, these are PhD students, and with help by undergraduate students. So sometimes maybe it takes a little longer, but it's incredible training for people to go out into the world in all kinds of things. One of the reasons NASA supports ballooning is not just for the science we do, but for the training we provide in being able to duct tape together a spacecraft, essentially, to do all aspects of this, from analysis, hardware. It's really neat. Now, what do we look for in students? Again, it varies. Our students tend to do a little bit of programming, so Python and things like that, to analyze our data and study things in the lab. We tend to look for somebody who's excited to work on hardware a little bit. Many people are a little afraid to turn the screws on something and see how it works. Sometimes I'm a little afraid to turn the screws on things in my own lab. But we look for people who are excited to give that kind of stuff a try. I don't know quite how to answer this, but you typically have people with a solid background in science and mathematics, a little bit of programming, and some enthusiasm for playing with contraptions, if that helps. Next, other questions? Comments, concerns? Yes?
Thanks so much for your talk. Are there ever artists involved in your exhibitions? Either videographers or, I don't know.
That's a great question. So the question is, are there ever any artists involved? And our project doesn't, our individual projects tend to not have artists per se. We don't have enough money to do what we're doing already. But one thing that the Antarctic program does do is it does have a program. In each Antarctic season, artists and writers are brought down to do their work. It's not just documentary filmmaking, though sometimes that happens, but to make art inspired by this thing that we're all doing. So I remember the first season I was down in 2014-15, there was an artist named, I'll get her last name wrong, but Lily, from Los Angeles, who it turns out her specialty was painting like really large, small animals, like huge paintings of like crustaceans or something. And so she got one of these fellowships to come down for the season, and she got taken everywhere. Like she got to go places I don't get to go. She got to go diving under the water and see things down there that she could then make art from. She was able to go look in the lava lake of Mount Erebus. Coolest stuff, you know. So yes, art comes out of this program, and it is part of what the National Science Foundation does try to do. There is a documentary film called Blast that was made by a relative of a PI of a previous balloon instrument that actually goes through a documentary film of a balloon campaign like this, which is pretty fun to watch. Yes, Matt.
The 160 gigahertz brightness of the CMB, is that something that we've been able to measure its change over time yet? And if so, how much is it changing?
That's a great question. So the CMB is a certain brightness at 160 gigahertz. Do we measure it changing over time? I think the answer is no. We have not done a measurement like that, and I can tell you why. So why is it? The brightness is best expressed as a temperature, 2.7 degrees with absolute zero. And the reason for that is when that light was emitted, the universe was sort of red hot, about 3,000 degrees Kelvin. And the universe is expanded by a factor of about 1,000, and so the temperature is lower by a factor of 1,000. So to get a perceptible temperature change, you have to wait until the universe expands a significant amount. So that takes, to be able to measure it you'd have to wait over timescales of millions or perhaps thousands of years. It turns out it's actually much easier to measure the place-to-place variation. It's much easier to measure tiny temperature differences across the sky than the absolute brightness. So it turns out our error bar in that number is 2.7255 or whatever, but we don't measure it to as many decimal places as this map might indicate. So no, we can't measure such variations with the technology we have now over the timescales available to us. But we do know from observations, I think, that I believe there are observations that tell us that when we look at objects in the distant past with our telescopes, we see that they are immersed in a warmer CMB. Because it was warmer back then. Yes?
It's my understanding that the universe is not only expanding, but it's accelerating in that expansion.
That's correct.
Was this determined by changes in the wavelengths? Or how did they determine that?
Right, so the question was the universe's expansion the universe isn't just expanding, that expansion is accelerating. It's getting faster with time. This was discovered around 1998 or 9 or so and led to the 2011 Nobel Prize in Physics. And the way this was discovered was by looking at distant supernovae, distant exploding stars, which appear, if they're very far away, they're moving away from us, and there's a certain class of exploding star that sort of always explodes the same way. And it always explodes at a sort of standard brightness. There's a few complications to that, but you basically have a boom of known brightness. And then you see how bright it looks, and that it gets dimmer as you get farther away. So that tells you how far away it is. And you can also look at the redshift to see how fast it is moving. And that gives you a chart to actually calibrate the expansion rate over time. And that's what allowed us to see that acceleration. The evidence of that on the CMB is pretty subtle, but we see it by looking at the redshifts and motions of objects. I don't know if that answers your question. Yes?
When you say the universe is flat, does it have a depth to it also?
Samar, what do you mean by a depth?
Well, is it just a two-dimensional?
Okay. So what do I mean when I say the universe is flat? I went over that pretty quickly, and it is a subtle idea. So all I mean by flat is, so what do we mean by flat in the real world, right? When you go in geometry class, back in elementary school, you learn that the angles of a triangle add up to 180 degrees. Okay? But if I was on the Earth's surface, the angles of a triangle do not add up to 180 degrees. If the triangle is really small, it's close, but you could build a triangle that goes from the North Pole to the equator, across, and back up. That would be 3 right angles. And it would look like straight lines. So on a surface curved like this, the angles of a triangle add up to more than 180 degrees. On a surface like a saddle, they add up to less. And you can extend that to 3 dimensions. So there is no depth to it, but it's harder to visualize, but you can also describe a 3-dimensional universe that has curvature. And the way, it's hard to visualize, but the way you would check is to make a really big triangle and see if how the angles add up. And that's essentially a version of exactly what we do with the CMB. That peak that we see, you're literally looking at the crests of waves crossing the sky, and that forms part of your triangle. And with careful calibration, you can see that it really does look like 180-degree angles. So when I say flat, what I mean is sort of space is not distorted in a certain way. I don't mean that it's actually a flat table. It really is 3-dimensional, indeed 4-dimensional with time involved. It's just very hard to visualize, but we mean something like that about triangles. Yes?
So when we're talking about a curved space, we're talking about local curvature, not global.
Yes.
Locally it's flat, locally it might have some curvature.
That's exactly right. So locally, the universe is curved. And we know that that's how gravity works. Einstein told us with general relativity that gravity is an expression of the curvature of space-time. And so the sun is curving space around us. To a much lesser degree, I'm curving space around me. So locally, you're right, the universe is curved. But globally, on very large scales, it appears to be flat. And that was something that we didn't know when I was a kid. And it was a big source of debate. And now it's very well measured from the CMB. It is as flat as we can measure. Again? Yeah, go ahead.
When you first, in your talk, mentioned that the Earth was proven to be flat, what observation led you to say that?
Yeah,
Refresh my memory.
I'm sorry, this was way back. This was that. The fact that the fundamental tone, the typical size of a hot or cold spot in the universe is about 1 degree of arc. That number would be different if the universe were curved. It's hard to sort of draw, but essentially it amounts to a certain way of drawing a triangle, and this is a way it would appear. If that peak were to the left or right of that, it would tell us about the curvature. And the fact its position is now so precisely measured, that's a real big triangle, and it really is 180 degrees. Yes?
Let's see. You mentioned that most of the radiation in the universe is microwave background radiation. Did I understand that right?
Most of the photons in the universe are microwave background photons, but they're not energetic photons.
Okay.
So there's various ways of talking about that. But if you had a box of the universe and counted the photons in that box, the majority would be microwave background photons, not star photons.
Okay.
If you make the box out in deep space. In this room, they're mostly light bulb photons.
Okay. But if you counted by energy, you'd get a different answer.
I would
I suppose.
have to double check, but yes, there's some subtleties to it. I don't want to say it wrong, but yeah.
I have another one.
Sure.
Practical one. So at the end of a balloon flight, how do you safely get the balloon down to the ground?
Yes, that's a great question.
Shoot it with a BB gun.
Yeah. So one thing I do want to note, I will answer that question. I can hang around and answer a few more. But it is half past, so if anyone wants to go, needs to go, do not feel bad. Thank you for coming. So yeah, if anyone needs to go, go ahead, but I'll keep answering questions for a few more minutes. Yes, so how do you get the balloon back? How do you deal with the balloon? It's, you can sort of see it here. That package right there, where did I put, yeah. This package here is actually a set of explosive bolts. The people who install that are these highly qualified NASA specialists who have these like explosive suits. And they go around in the special suits to install that one component. It's a big deal. I should not be as close to that as I am taking this picture. No one tell anyone. But what happens is there's a GPS system, there's a satellite communication link. When the payload looks like it's going to head out over the ocean, or it's the mission is done, or if it's just in a particularly convenient place to recover such that it's not worth continuing, they send a command, that blows up, it tears the balloon, and drops the payload on its parachute. So the balloon lands right nearby. One other version of this question people sometimes ask is what happens to the balloon? The balloon isn't shown here. It's a little off, it's like a mile away. It's 22 acres of saran wrap covered in snow. And it weighs several tons. It weighs more than the payload. So we have to fly out, not we, but people have to fly out in little twin-engine planes to pick this stuff up. The balloon is generally, in Antarctica, it is hard to safely recover the balloon. So we leave clean snow here, but the balloon itself is sort of marked and left buried on a map. Because it's just, you would just shred it trying to remove it. You do more environmental damage trying to pick it up than you would leaving. Other than that, we have treaty obligations to leave the snow clean, and we do, but the balloon is sometimes an exception.
And the payload basically gets drug along the ground.
Ideally not.
Okay.
but yeah, the parachute is designed to sort of, on impact, also tear in a way that it doesn't drag the payload. There was a famous incident in 2006, I want to say, where that didn't happen, and the payload actually bounced and dragged in high wind for many miles and left pieces all over, and it was not good. But they found the data disks. Fine. That appears in this video. There's a section where, so the data disks, traditional hard drives, have to be kept in a pressure vessel. They actually require air to operate because of how the hard drive head floats above the disk. So you have to keep them in a little pressurized tank. And everything on the gondola is painted white because of the sun. You see the problem if pieces start falling off in the snow and they're painted white, and you need to find them, but they did. It was a big deal. Question behind?
For that other style of ballooning that you mentioned, the newer one, is the balloon able to be recovered for that, or does it get lost as well?
In general, the balloons are recovered. It's an exception for certain places in Antarctica where it is difficult, and it is safer to leave it. But in general, the balloons are recovered. Sometimes a payload will drop into the ocean. We try to avoid that. It is more of a risk for the superpressure balloons than it is for these. But in general, we are an environmentally conscious program. We don't leave messes. Most balloon flights, there are balloon flights from Fort Sumner, New Mexico, that are just overnight flights, and they kind of, land someplace in New Mexico, and they send a truck, and they pick it all up. And that's how it goes. Okay, yes?
So do you also have students analyzing all that data? Is that
Yes,
part of
we're kind of ramping up. Do we have students analyzing the data? Yes. There are, it's a little bit of a slow start coming off of the campaign, and there's always the competition between working on the next instrument, analyzing the data from the last one. But yes, the current progress on that, we're working a lot on, so my student Ellie, who just graduated, worked a lot on the camera sensitivity, which I showed you. The next step is pointing, is producing an understanding of where the instrument was looking at every moment to build up that map. And one of our very important pointing sensors actually failed on launch. We have plenty of redundant pointing sensors, but making those all work is a pain. The easy sensor didn't work, so we have to use the hard sensors. And so it's just more work than we thought, so I can't show you a map. But yes, this is an active area of research and will be for a couple of years, I would guess. Okay. If there are no other urgent questions, again, thank you all for coming, and yeah, enjoy either exam period and/or the holiday season, depending on what comes next for you.